Hey, let's begin chapter 6. Chapter 6, applications of integrals. Really, chapter 6 is just a natural extension of what we started in chapter 5 in the way where we're at after chapter 5. 6.1, we'll look at areas between curves. Notice 6.2, I divided up into two parts. We start looking at volumes. So taking areas to the next dimension, we'll do volumes in 6.2 and in 6.3. And then 6.5 will wrap up with the average value of a function. So let's get to it. 6.1, the areas between curves. What if we did not simply want to find the area between one function and the x-axis, but the area, say, between f of x and g of x, right? Like that area right there between the purple lines. How would we do that? You think, well, an integral always finds the area between the function down to the x-axis. So what we could do is this, to find that area that we're looking for, we could find all of the area beneath f of x all the way down to the axis. We could find the area under g of x between the green line and the x-axis and subtract them, right? All of that area under f, subtract that area under g, and what's left? Just the area between them. What would that look like? So, well, the area under f is your integral from a to b f of x dx, your area under g, the integral from a to b g of x dx. But because they have the same limits of integration, because they're both integrals from a to b, we could combine that into a single integral by subtracting f of x minus g of x, like so. And so think of that, that's like our formula for how to find the area between curves. One important thing to note, remember that it's always the function on top minus the function on bottom, right? Here, f is the top, g is the bottom. It's always top minus bottom going vertically. There will be some examples, where we just want to keep that in mind. Okay, one other thing. In the picture you see at the top, right? This is all in the first quadrant, or everything's above the x-axis. What would happen if maybe one of the curves or even both of the curves goes below the x-axis? Maybe something like this. Here, f of x is above the x-axis the whole way. But g starts off above, but then dips below, right? And we remember that any area below the x-axis is thought of as negative. Well, when we say we're finding the area between curves, our answer is always going to be positive now. So, before, even though we thought of a definite integral as being an area, we allowed negative answers. When we find the areas between curves, we're always thinking of it as positive area. So it turns out our same formula will work just as well for this picture. Why is that? Well, you think, okay, well, f of x is finding all the area, under f, subtract g of x. If g of x is above the x-axis, then we're subtracting that little bit of area here, and it's all fine for this kind of section. As soon as g of x drops below, we actually still want to subtract, because then we're subtracting negative area. And so it's adding it on, and we get all the positive area, the space that takes up, the area between them. So subtracting is actually what we should do since it goes negative. Okay, perfect. So the takeaway is this is the only formula that we need for finding the area between curves. And we remember it's always the top minus the bottom. Okay, very nice. From here, we just got a bunch of examples. These are going to take time, especially some of the later ones. So we'll find the area bound between the curves. We'll start off, just with a polynomial and other linear functions. And we'll look at, something involving a square root, some trig, and then finally this last one will really mix things up for us. Okay, let's check out part A. Find the area bound between the curves. We're looking at the curves being y equals x squared plus 4, y equals 3, x equals 2, and x equals 5. This is the way that problems are going to be presented to us. There's going to give us a list of the functions or the list of the curves. Okay, when you get one of these, the first thing we're going to need to do is take a look at the graph. Maybe here you would more or less know how to graph each of these lines. I'm going to jump over to Desmos and definitely recommend this as things get more complicated. But even for the simple ones, why not? We've got y equals x squared plus 4, so we got this parabola. They also said y equals 3, just a horizontal line. X equals 2 and x equals 5, these two vertical lines. So we can see that shape right in here. Okay. One of the skills in this section is learning how to identify, based on the list of functions they give us, learning how to identify the region, even once we have the graph. You would think like, well, that's no problem, right? I mean, how difficult could it be to identify what the region is? That's what I used to think when I first started teaching calculus many, many years ago. And then I realized, you know what, sometimes it's not as obvious to students who are just learning this as I originally thought. So here's kind of some guidelines to identify the correct region. Make sure the region you're looking at touches all of the boundaries. All right, so what region here would border each one of these 4? And it turns out it'll be this space right there. So it's got x squared plus 4 on top. It's got y equals 3 on the bottom, and then the left and the right are bordered in. Okay. Once we've got this region graphed, I'm actually going to sketch that on my page, and maybe if I can adjust the scaling, but I'm going to more or less sketch that parabola and all these other lines. Let's do that. Okay, so we've got an XY plane here. The parabola is going to come in. I know I'm focused more on the right side of this parabola, so I'm going to draw this. There's y equals x squared plus 4. It goes through. This is important. I should label this. That's at 4. Okay, I also know I've got the line at y equals 3. So it's this horizontal line beneath. Let's say 4 is there. There's 3. And then we've got these two vertical lines. One of them is at 2. The other at 5. So this will give me a good enough picture of what's happening. Now, again, which region is it? It's this one right here. This region is touching all 4 of my boundaries. Okay. Once I have that all set up, then I want to remember my integral formula. So I'm going to call it area equals integral. Let's think first, what would be the limits of integration? What are the a and the b? So looking at that, well, it's going to be those x values at 2 and at 5. That's my starting and stopping. And I'll put a bracket. Which function is on top? Well, it's obviously the x squared plus 4 minus, and which function is on bottom, and it's just that horizontal line at 3 bracket. I put a lot of parentheses here just to highlight. There's my top, there's my bottom, and the limits of integration to starting and ending points. Okay, once I have this together, I can simplify. I'd suggest cleaning it up before you do an antiderivative. Clean it up as much as you can. This will be x squared plus 1. Then perform your antiderivatives. 1/3 x cubed plus x, evaluated from 2 to 5. And finally plug in. Simplifying it first, just gonna make your life a little bit easier to get an antiderivative, maybe. Definitely easier when you go to plug in. 1/3 times 5 cubed plus 5 minus 1/3 times 2 cubed plus 2. And let's see, maybe I'll do that whole thing at once. 1/3 times 5 cubed plus 5 minus 1/3 times 2 cubed. And I can even think that minus sign is going to distribute minus 2. I got, turns out it was a nice whole number there, 42 is that area. Exactly. Okay. The key here, right, once we get to the point where we have the definite integral, you know, then it's just like a problem from back in 5.3 with the fundamental theorem. Where you want to put your attention is in the drawing, figuring out which region it is, and then setting it up. A mistake in the drawing and the sketch, or a mistake in which region it is, gonna lead you to bad places. So make sure those are dialed in. That's, again, that's where our attention's at. All right, part B, let's check this out. Y equals x squared and y equals 8 square root of x. Maybe I could sketch this by hand. I'm going to jump into Desmos. No reason to guess. Make sure I get it right. Y equals x squared and y equals 8 square root. You type in SQRT. I don't know if we mentioned that before. All right, there we go. Notice kind of what's the big difference here, right? They just gave us these two functions of y. They didn't give us any vertical lines. When they give us vertical lines, like in the last one, x equals 2, x equals 5, that's probably, you know, if not always, going to be the limits of integration, where to start and stop. They didn't do that for us here. So where do we know where to begin and end? Well, once we identify the region, and it's going to be this kind of teardrop sort of shape there, we say, okay, it's wherever these two curves intersect. That's our starting and ending point. Now from the graph, maybe we can even see where that happens. Well, one's at x equals 0. The other is at x equals 4. And we could confirm that, like 0 is pretty clear, they're going to equal each other. What if we plug in 4? Well, that first curve is going to be 4 squared, 16. The second curve, 8 times the square root of 4, will also be 16. Yep. So visually it seems clear enough, but just to plug them back in and confirm, yep, they both are at 16. Okay, let's graph this, shade the region. Square root looks something like that. X squared, something like that. Y equals x squared, y equals 8 square root x. We note that this is the region, what's in between them. All of the regions, by the way, they're all going to be finite. So if you're ever shading a region and it's infinitely large, that's not it, right? We're like, would it be this space up here? Well, that touches both of them, right? Well, yeah, but that's an infinitely large region. Like we're not ever going to do that. Okay, we notice they cross here at 0 and they cross here at 4. We could note that it's at 16, although I don't think that's necessarily going to help us. Okay. With this, we've got a good drawing. We've identified where they intersect. Let's find the area. This integral is from 0 to 4. Which function is on top? Top minus bottom. It's the square root. Occasionally people mix this up because they're like, well, top and bottom, right? Well, no, because they crossed each other. So there's the top, 8 square root x minus x squared. Okay. 8x to the 1/2 minus x squared. Here we go. Let's see. That'd be x to the 3/2. If we divide, 8 divided by 3/2 would be 16 over 3. Multiply the 3, that would cancel. 16 over 2 is the 8. Yeah. Minus 1/3 x cubed. This is from 0 to 4. And plugging in 16 over 3, 4 to the 3/2 minus 1/3, 4 cubed, minus 0. Hey, plugging in 0, 0, 0, that's all going to be 0. Be careful when it comes to plugging in 0. Sometimes we can get lulled into thinking, oh, plugging in 0 is always 0. Well, not always. For a polynomial, yeah, but not all the time. Okay, let's see. Putting this in, grab my calculator. 16 over 3 times 4 to the 3/2 minus 1/3 times 4 cubed. 64 over 3. We got it. The exact area, 64/3. I mean, who would have thought that that area would come out so nice? 64 over 3. Exactly. Wow. Okay. The question you may be having is, what if, we were doing this sketch by hand, let's say, we didn't have technology to work with, or, we wanted to figure out where these things intersect. You could figure out they intersected 4 if you set the two functions equal to each other. Do that and solve for x would be another way. Here, you'd have to square both sides to get rid of the square root. So you'd have x to the 4th equals 64x. Then subtract, factor out. And it turns out this would factor further, or actually, no, you could go ahead and solve at that point. So you'd get the x equals 0, x cubed minus 64. You could do it right here. X would equal 4. So you'd have both your points of intersection. If it comes down to it and you just want to confirm you've got the right position, you could always look to solve. Sometimes that's going to be easier to do than others. Okay. But the point is, maybe we can get that number just graphically. If we can visualize it, then we can plug in and confirm that they both give the same y value. Again, like all of our focus goes into the drawing, getting the region right, and then setting it up correctly. From there, now it's just a definite integral problem. Okay. Let's look at one more. Let's do part C in this video. Y equals cosine x, y equals sine x, x equals 0, and x equals pi. Again, we're going back to having some vertical lines. Something gonna be different about this. Let's check out the graphs. Y equals cosine x. Okay. Y equals sine x. X equals 0, right? And x equals pi. Interesting. Notice what's happening here between the red and blue lines. Right, we can see sine here in black, cosine there in purple. Notice they cross each other while they're between those vertical lines. So these lines are telling us where to start and stop. But what's going on here? They, at first the black is beneath, but then, they switch. There are actually two regions. There's this region here, which touches these three, and there's this region which touches now the blue. Let's graph that by hand. Actually, and we'll just go ahead and put pi right there. Here's pi over 2, and maybe we'll even do a couple more. All right, so cosine starts up at 1, comes down through pi over 2, and by the time it gets to pi, it's at -1. Sine starts at the origin, comes up here at 1 when it's at pi over 2, and then by the time it gets to pi, it's back down to 0. And then we have this vertical line as well. Trying to avoid hitting my camera with my pencil. There we go. So we got x equals pi. Here is x equals 0. Y equals sine x, and y equals cosine x. Like I said, there are two regions. There's this region, and there's this region. They cross one another. Why do we need to do it this way? Well, there's no other region to pick there is no way to touch all four of them and still have a finite area. And so the giveaway is if they cross one another. Okay. Then our next question is, well, where do they cross? And it turns out that's at pi over 4. I had to adjust my line there a little bit. So how are we going to do this? If we've got two regions, we're going to need two integrals. The first integral is when cosine is on top, sine is on bottom. The second integral is when sine is on top, cosine is on bottom. There's no way to do that as a single integral since they cross each other. Let's see how we're going to go about this. Let's call that area 1. This is area 2. Let's do it like that. So area 1, and then we'll add them together in the end. Area 1 is the integral from 0 to pi over 4. Here, cosine is on top, sine x is on bottom. Okay, let's figure this out. So area 1, antiderivative would be sine x, positive sine x. The derivative of cosine is negative sine, so that's plus cosine x. And this is from 0 to pi over 4. Let's see, plugging in, we've got sine pi over 4 plus cos pi over 4 minus sine 0 plus cos 0, 0. Let's see here, sine pi over 4 is root 2 over 2. Cosine pi over 4 is also root 2 over 2. So well, maybe I should just write it out. Root 2 over 2, root 2 over 2, minus sine 0 is 0, cosine 0 is 1. These added is simply root 2 minus 1. There's area 1. Okay. Area 2 goes from pi over 4 to pi, and now sine is on top. Sine x minus cosine x. Antiderivatives, let's see. Derivative of cosine is negative sine, so this must be negative cos x minus sine x. Be careful with your negatives and positives. From pi over 4 to pi, okay. I'm just going to think about these being plugged in. Plugging in pi. Cosine of pi is -1, but then another negative makes it +1. Sine of pi is 0. Pi over 4, negative root 2 over 2, minus root 2 over 2. So area 2 is 1. That's negative root 2, 1 plus root 2. So the total area, area 1 plus area 2, right? Add them together. We had root 2 minus 1, kind of interesting, plus 1 plus root 2. What's that going to be? Ones cancel out. It's 2 root 2. Wow. There you go. So it worked out actually fairly nice in the end. Fairly simple. Exactly 2 root 2 for the total area. Here's kind of an observation. Just to wrap up this question, is something that's kind of interesting happens. Notice there's some symmetry, right? This little region here is exactly this part. Right? We found this region to be root 2 minus 1. So this would also have to be root 2 minus 1. What would that mean for the rest of that area? What would the rest of that area be? Right, we had the total is 2 root 2 for the whole thing. So if everything is 2 root 2, and this is root 2 minus 1, root 2 minus 1, right? These two added together are the 2 root 2 minus 2. This whole thing would have to be 2 in order to cancel out those minus 1s. Okay, what's the big deal? What's each one of these then separately, right? There's like a top half and a bottom half that are identical. If the total is 2, then this is 1 and this is 1. Think about that. This shape right here is exactly 1 unit. What is that? I mean, that's the area under sine from pi over 2 to pi. Or even here, you know, that's the same shape. That's got a 1. This is a 1. If we continued to draw sine all the way to 2 pi, that would also be 1. Each one of these quarters in the sine graph, same thing for cosine, that's 1, right? Like, so each one of those is just kind of interesting that the area of a quarter of the sine graph or the cosine graph is exactly 1. It's kind of, you wouldn't think that exactly 1 square unit. I mean, it's 1 unit tall, but because it's pi over 2 long, like, okay, that's really bizarre. Anyway, I think we've done enough for this video. Let's do that last example. It's a little bit different. We'll do that in the next one.